What?
Is it not recorded with that?
It's not working now.
Then how is it getting recorded? That's how it's. Yeah. Maybe I should hold it. Huh? Maybe I should hold it.
I'm gonna come like in my face and stuff.
Yeah.
All right. Let's settle. Everybody. Start back up. We have a lot to catch up on. I can barely hear myself. Use the microphone. Oh. Okay. Not again, not again. Not now. Okay. So we want to make it towards the last step of the course. So I'm going to go really quickly through linear transformations, and then we'll start with determinants, invertible matrices, Cramer's rule, joint matrices, eigenvalues, eigenvectors, coordinate vectors, all that stuff. Okay. All right, linear transformations, really quick. Is it part 4 of the course or part 3? I don't know. Part N of the course. Linear transformations. We have about 7 things: image, range, inverse image. Who said oh no? Why?
It's confusing still.
Yeah. I'm just gonna go through these intuitively. That's it. I'm just gonna explain it in words because I know it's confusing, and so you guys can replay the recording over and over. I guess till it goes through.
Okay.
I don't know.
Wait, what would be the timestamp though?
I'm kidding. I'm kidding. Injectivity. Surjectivity. Bijection. Thank you. And then invertible. Okay, quickly.
What about matrix?
Matrix is later. So image.
Wait, isomorphism.
Yeah, isomorphism will also be later. You can add it if you want to. Okay. No more? Yeah. I'm gonna ask you questions. I would say image, I just wanna, because this is something that I got a lot of questions about in Algebra. It's just, image is set of elements in V or W, where T, select T, V from V to W. Will the image be in V or W?
W.
W, right? Okay. W. Will the range be in V or W? W.
Yes, same.
Will the inverse image be in V or W?
V.
V.
We are same though.
What about the kernel? V. You guys sound bored, but then a lot of people get it wrong. Like, come on, maybe the smart people are here. I don't know. Okay. Injectivity. How can we show something's injective?
Show that that the image, or I guess the range, equals the entire vector space.
Or we could show that TU equals TV implies U equals V.
The kernel is 0.
This is not enough to give you full marks. You can't just state this.
No,
Kernel is
kernel equals 0.
That's all. That's also another characterization. Yes.
Oh, I got them mixed up.
Yes. But when you say this, this is something that I saw in the most recent assignment up till now. When you say this, it's not enough. You can't just end here. Okay? Yeah, obviously for all U and V, but you actually have to work with T. People just tell me TU equals TV implies U equals V, Q and V. And this doesn't hold for all linear transformations. Yep.
Is kernel equals 0? Kernel T equals 0 enough to show that it's injective?
Yes.
That is enough.
Yes, that's enough. Yes. Yeah. Yeah.
So why is like showing the kernel is only 0? Right?
When the kernel is only 0, you're given injectivity.
Like, let's say, like, even though, like, 0 max, like, 0 in W, but there exists 2 elements in V that map to 1 W, and then it's not rejected. Right.
And the kernel's not 0.
There's other things in the kernel.
Like,
It's a theorem, so, okay, assignment for calc, find me a linear transformation where the kernel is not 0 and it's injective.
no, I
That
read
makes
that.
it really zero.
Be here for a while, I think. Okay, surjectivity.
The codomain.
Guarantee equals dimension.
How can I characterize surjectivity?
The range is the
Okay, bijection is just something plus something, which is injection plus surjection. Okay, invertible follows from
Bijection.
and then an isomorphism. How can we show two things are isomorphic?
Linear bijection.
Show that there exists a bijection.
What's the difference between bijective and isomorphism?
The same thing. So isomorphism is well, this is gonna go into stuff that's later. But for now, you can show that there's a bijective map, and you can say two things are isomorphic.
So, like, what's the, like, how are they different from each other? Bijective.
Here they're the same. They're the same.
What about like image and range? Like, what's the difference between?
Yeah, good question. So what's the difference between image and range?
one is for subset.
Yeah, one is for all subsets. Range is whatever our V maps to. So just T of V. That's it. Okay?
So
So
all subsets.
that means we're talking about the image of any subset. Let A be a subset of V. So let A be a subset of V. Image of A is the set T of A, set A is in A. Right? But the range, you're not taking the range of a set, you're taking the range of a transformation. So you say range of T is equals to T of V, where V is in your entire domain. Domain is just V, right? So that's the difference. Any questions about it? Yeah?
Isn't it like the opposite?
For what?
Like range is everything in V that gets mapped to W. So all the subsets, and then image is just one of them.
Yeah, no, I'm saying when we're talking about image, we're talking about a particular subset. So we take the image of any subset. But when we're talking about range, it's really just talking about one thing. Right?
Oh, everything in V.
Yeah, everything that V maps to in W, right? Okay, good question, no? It's important to make these distinctions, you know, the worst thing is to make a mistake on something that we went over 70 times. Okay. Don't think I have questions still about this, because we should be good with it otherwise. Yeah, okay. So no questions about linear transformation? Yeah, question? I'm sorry, I can't hear you. Is that equals to the range of T? So the question is, if A is a basis for V, right? A basis for V. And what was that? What did you say after that? Image. Image. So you want to take the span of the image, right? Span of the image of A, and you're saying that's equals to the span, or equals to the range? Is this what you're trying to say? Yes, because it's linear, right? So you'll just keep taking in the scalars and you can represent it as any element, right? Yeah. So yeah, good observation, good question. Yeah. Do we all understand what the question's asking? Okay. Let's move on to matrices now and determinants. Okay. Now we are in part n plus 1 of course. Alright, so let's go. What's the row space? Span of the rows, right? What's the column space? Span of the columns. I wish everything was as obvious as those two definitions.
Right.
Okay, now let AC denote the column space. Is AC a subset, or sorry, subspace of Rn or Rm? So if we have AC, yeah, is it a subset of Rn or Rm?
Rn.
And then AR is a subset of Rm. This is important because we have our rank nullity theorem that relates to our dimension kernel theorem, right? So let me find a board that I can use. Are we all good to erase this?
Yes.
Question?
Let's say Rn.
Which one?
Yeah,
This
that-
one?
that's
I mean, if this is n,
Yeah.
what would this be?
M.
Yeah.
Okay.
I appreciate the questions, Kyle. Okay. So true or false, really quick. Any So any transformation or linear transformation could be represented by a matrix. True or false? Hands up for true. Hands up for false. Derek raised his hand.
Wait.
It is false.
Doesn't it have to be? It has to be n by n.
Not
No.
quite.
Linear?
Yeah, huh?
It has to be linear.
It is, well, I said it was linear by one. Why is it false? I like the comments, good. Yeah.
Then like the all zero one.
No, so the problem is with any. We could separate this into a particular class of transformations, linear transformations. Yeah, so I don't get corrected again. Yes, I like the thinking face. That should work. Yeah. A bit more specific.
To find
Okay, so maybe this will give you a hint. Yeah. Oh.
One that maps, one that I'd say backwards shift, it can be represented by the matrix.
Okay, I'll just give you the answer. This is false, but it's because only linear transformations T from Rn to Rm necessarily have a matrix representation. Okay.
So like both of them have to be fine, right?
You could do it for other, but it's it's not necessarily true that you always have a matrix representation.
Wait, what about?
This is the only case where it's necessarily true.
Wait, I thought we should always.
No, not always.
Wait, what did you say?
So for real vector spaces.
You're losing the class.
Right.
Yeah. Hands up. Okay, Nicholas. Somebody asked that in tutorial and it said we're not responsible for it because we're gonna get into stuff that we don't need to know. Next question. What is it?
For it to be false, is not only one of them or does not be both?
No, we can only say it's necessarily true when T is from Rn to Rn.
Both have to be one.
Wait.
Both have to be from Rn to Rn. Yeah. Yes, question.
So for like real value transformations, so like real in the field of reals.
Yeah, that's when we can guarantee a matrix.
So it's not always a guarantee if we have any other field.
Yes. Yes. Next question. Maybe it's controversial, true or false question. Abdurrahman.
Yeah, you said that it only has to be linear transformation from Rn to Rn.
It's not only. The only time where we can guarantee that it has a matrix representation is when it's from Rn to Rn.
But what about
There.
when we said like P of NR is isomorphic to Rn?
Yeah.
And we can write a matrix representation in
Yes.
a coordinate basis.
Yes.
Yeah, and it's still real.
Yes, but that doesn't mean that you can always guarantee. The only case where you can guarantee is when it's like this. Any linear transformation will have a matrix representation. But give me any other transformation, it's not guaranteed. That's all I'm saying.
Okay.
Yeah.
Excluding one-dimensional abstract vector spaces that are isomorphic to Rn.
No comments.
How does isomorphism fit into this? Is my question.
Isomorphism do fit into this. As Abdurrahman said, yes. When you take isomorphic things to Rn to Rm, yes, it would hold. But I mean, maybe I should say up to equivalence with isomorphism. I guess that would make it more specific. But did we take equivalence classes with isomorphisms? No.
Yes.
So yes.
Wait,
Exactly.
Wait, can you put up the counter example?
And you asked me for a counting example when I put it up too in tutorial. I said we can't do the counting example because it's out of the scope of the course. If you want, just look up a counting example, a linear transformation which does not have a matrix representation. Okay, so it's supposed to be a fun true and false turned into me getting blamed. Okay. Okay.
Can you not do the TJ data group?
Okay. Next up, we will cover. Did you guys cover this?
Yes, we did.
Yeah.
Yes.
Did we also cover rank nullity?
Yes.
Column space. Yeah. How could we relate these two?
By diamond.
Huh?
They're the same. Well, like one's for matrices and one's for like non-matrices.
Yeah, and so this is how we relate the linear transformations from Rn to Rm and matrix representations of them, right? So these two look eerily similar, right? We have the kernel and the nullity, which sort of describe the same thing. Don't say they are exactly the same thing, because it's talking about vectors. And then the dimension of the range and the column space, and then finally the dimension of V, which is the amount of columns, which here would be Rn, and so it's dimension n. Okay, I just wanted to give you guys a brief little overview on that. It's covered in my tutorial, but I don't know if all people covered it. Okay, erase this? Okay. Now, we like to ask the question when something is invertible, whether it's a linear transformation or it's a matrix. And we just saw the relationship between linear transformations and matrices, and we already talked about the characterizations of invertibility when it comes to linear transformations. So, what characterizations do we have for invertibility when it comes to a matrix? Raise of hand, and then I'll pick a few. Okay, so let A in M, N, R. A is invertible. Then, so if A is invertible, then what's the first thing? Usually.
Row equivalent to the identity matrix.
Okay. Second one. Yes.
It's bijective.
It's bijective. Kind of the same thing as this, but you're saying we're talking about the matrix.
Oh, it's determined getting 0.
Yes.
M should be split.
Or is it?
M should be split.
That was the one that I didn't think anyone would get. Yeah. Next. Kyle?
I was gonna ask, for the rank knowledge, right?
Uh-huh.
How do you calculate column space or column thing?
So you just, it's the column space of A is, the column space of A is the span of the columns, and then you take the dimension of that, and that's called A.
Yeah, then it should be
Okay.
dimension of column space of A.
Yeah, you're right.
And then how do you calculate range of T? Just makes like a 5-year-old.
Okay. So let T be from Rn to Rn. Okay. Let's send X, Y, Z. Actually, let's do R3 to R3. So X, Y, Z, X, 0, 0. What's the range of T? 1. No, what's the range, not what's the dimension? Yeah, the range is span of 1, 0, 0. And so what's the dimension?
1.
Just 1, right? Okay. Okay, back to our characterization. I think we're missing 2,
Full range.
at least for now. We have more. There's like 10 actually.
Yeah.
But we didn't take all. Yeah.
So column space linearly independent because of linear independent.
Things you have. I didn't know.
You could say like range of A equals M.
What about the actual definition? So there exists
Here it is.
M such that A is M, I, V I. I think I'm running out of my Roman numeral knowledge. Okay, I think that
Shouldn't
that's,
it also be NA?
yes. The multiplications come to the same. Well, no, actually it's not matrices. Okay, all good? Question?
I think there's not trivial things.
Trivial numbers, yeah. AI and x equals 0 if and only if x is equal to 0. Okay, and this is, they're all equivalent, and you can actually prove these, but we're not going to prove they're equivalent. Not going to help us now. So when they ask you to show a linear transformations invertible, you could turn it into a matrix and then show that any of these hold. Okay, when our linear transformation could be represented by a matrix. And you can only guarantee that when what I raised, T is from Rn to Rn. Okay? Good?
Yes.
Questions? Yeah.
And if it's not from Rn to Rn, it might exist, but it's not guaranteed.
It might exist, but it's not guaranteed, and you're not responsible for representing it. If we do give you a transformation from not Rn to not Rm, you're not responsible for knowing how to represent it as a matrix, because the question is you're gonna have enough tools to solve the question without that.
Wait, what? Didn't we do beta to C?
Questions? Yep. Yeah. So column space linear independent is essentially saying full rank,
Yeah.
right?
Oh.
Right?
Yeah.
So if the column space is linear independent, that's kind of saying the same thing that's row equivalent to I. Right?
Yes.
Yeah. The first one is my personal favorite.
Yeah, I wonder who.
Wait.
Yeah, I wonder who
It's
says. It's
You're saying that as dependent, right? Conflict is dependent. Like,
independent.
independent. You just ate the right.
Yeah.
Did you say eigenvalues are not zero?
Yeah. So that's one of them, but we didn't reach eigenvalues. Yeah, good job. I think we should move on because we don't have much time. But questions, 100% after. I'll be here. Okay. Let's do a computation problem because that's most likely what you're gonna see on. I don't know. I haven't seen the final. Now you all just leave. No, I haven't seen the final. But I'm taking courses or a course with Korea before, so I kind of
oh my
can
god.
expect that there will be one computation problem at least.
He said there was gonna be a one hard one, super hard.
Super hard?
Yeah. He scared me.
Oh no.
What?
Question number 5 or something.
Determinant
Wait,
of.
I thought you, it
Yeah,
was
he said there was.
between a group or a hard computation.
No, he said you have to do both.
Wait, what?
Yeah.
Which one are you supposed to choose?
No, you do both.
Oh,
Yeah.
Okay. 4x4 matrix, determinant,
Oh my.
right? Looks ugly, but it's not. Right? Why is it not ugly? Why can we do this really fast?
There's a lot of zeros.
Right? So we notice that there's something very nice. These are all zeros except one. And so let's expand upon this one. Right? So which column is this?
Zero.
Three.
The first column.
First
Which column?
First.
Second column. Which row?
Third row.
Third row.
Third row.
Third row, second column, right? So minus 1, 3 plus 2 times 1, right?
Yes.
Times, and then we delete this row and this column. That's third row and the second column. And
One,
we get
zero,
1, 0, 5, 5, 0, 7,
6, 9, 8.
7, 6, 9, 8. And again, 3 by 3, but our life's easy. Why?
The second row, zeros. The second row.
Yep.
Wait, shouldn't that be -1?
Where? Negative 1?
Oh, never mind. Oh, yeah, sorry.
Yeah, this is negative 1 to the power of 3 plus 2, right?
That's
So
fine.
9,
And so now we have equals to negative
9
1,
45 plus
3 plus 2 times second column, third row, negative 1, 3 times 9 times the determinant of 1, 5, 5, 7. 1, 5, 5, 7. We all know how to do this. This is negative 1, this is negative 1, this is 9. So that means this is just negative 1 times negative 1 is 1. So 1 times 9 times, how do we get the determinant of 2 by 2?
Last problem.
1 times 7, and then minus 5 times 5.
32.
Yes. So 1 times 7 minus 5 times 5. Right? Which is equals to 9 times minus 18, which is minus 162. Okay? So whenever you get a big ugly determinant, just try working on expanding the row that you, or the column that you find with the most zeros. Okay?
How do you know that maybe 1 is equal to?
That's the formula you're given for determinant. When you expand upon the second column in the third row, you have to multiply by a factor of -1 to the power of 3 plus 2. Question on that?
Not the triangular one. Are we allowed to use like if it's not the triangular one, are we able to do like both one back? What?
You could expand it upon the last row, which will
talked about in the lecture, like if it's symmetrical, then we then instantly know that it's convertible.
If it's symmetrical.
Oh, we know it's diagonal.
Yeah. If it's that, yeah, that's
No, it's all
diagonal.
diagonal. If it's symmetrical, then it's diagonal as well.
Oh yeah. If it's symmetrical, then it's diagonalizable.
Yeah.
Okay.
I'm not even sure what the question is.
Okay. Yes, but not matrix representations. And I'm going to do example on that, so it's fine. Okay. Kramer's rule.
Oh, yeah, that. Oh, no, I forgot it.
I think Kramer's rule, I don't think we have enough time. I think we have enough time for one example for that, and then we're going to have to call it a day. So do you guys, I think it's the better thing if we move on to coordinate vectors, inner products, norms, eigenvalues.
Diagonalization.
Yeah.
Go to eigenvalues.
We'll try to reach whatever we can reach. I have 20 minutes left. Okay, so coordinate vectors. What is this, n plus 2?
You mean unpacked?
True or false? There exists a subspace W. These are vector space such that V, if there exists, V of B equals V of B prime for all ordered bases then W is trivial, i.e. 0. Wait, not for all ordered bases, for any two ordered bases, for two.
What if B prime?
Another ordered basis. So B and B prime are two ordered bases, and if there's a subspace such that V of B is equal to V of B prime, I forgot to mention for all V in W, then W is trivial. True or false? Hands up for, well, I'll let you guys think about it for a bit.
Does trivial include itself or just zero?
Just a 0. Question or answer? Yeah. Oh, okay. For two ordered bases, yeah, this was a bit small. A C's, B and B prime, then W is trivial.
Do we assume B and B prime?
Yes. So hands up for true. So this is for all V in W. Hands up for false. If you say false, you're gonna give me a counterexample. We don't want speculation. That's 1 out of 3 on the true and false. What about the justification?
Wait, what?
So it is false, you just said.
No. Maybe. It is false. Okay, hands up for false.
Oh, no, it's false.
Yeah.
False.
Yeah, it's false. Why is it false?
Because it could be like an OR basis of like one x squared and 2x squared. Where you basically just only change one or like one that's inconsequential.
Yeah, so let P2R, let B equals to 1x squared, and then B prime equals to 1x squared x space be, so let W be the span of 1, 0, 0. You guys see how? Yeah.
Wait, can you say that again?
So let our first ordered basis be 1x squared. Let our second ordered basis be 1x squared x. Let W be the span of 1, 0, 0, so it's all real numbers. Right? For any two vectors in W, the coordinate vector for B and B prime will be the same.
But will they not be the same? They will be in a different order. No.
No, because those are always going to be 0, right?
The only thing that matters.
Oh,
is
the
only
only
thing
thing
that
is the
matters
first
is
one.
Yeah, yeah.
Oh, okay.
Yeah. Thank you. Thank you. Okay?
Yeah, because there's something that says that it's gonna be unique always, the current vector.
Yeah, but here I mentioned that it's a subspace, right? So I'm saying, does there exist a subspace? Well, if there exists a subspace, then it's trivial, and I'm saying no. There is a non-trivial subspace. Okay?
Wait, what triangle basis mean?
Are we all good? Like, do we all understand
What triangle basis mean? What triangle basis mean?
I'm sorry?
Triangle basis mean?
Trivial basis, trivial, W is trivial means W is 0. W is equals just the same, 0. This is what it's trivial means.
How do we get the W span 1, 0, 0?
Yeah, I'm saying there exists a non-trivial subspace.
What does dot notation mean again? Does where brackets are on?
This is the coordinate vector. So the coordinate vector of x squared plus 2 plus 1, I don't know, what would it be? Or 1 plus x squared, what would it be? So let p of x equals 1 plus x squared. P of x, coordinate vector with respect to b, is equals to 1, 0, 1, right? 1, 0, 1. Right? It's just the scalars we need to get our vector. Right? I just don't want to like regurgitate the definitions over and over. Just like, we don't really have to. Question?
Yeah. Don't we need a transformation to like find them? Or is it not necessary?
No. Coordinate vectors just need a basis, right? So I guess this is something that we do need to revise when we go home. Okay. If it's like, yeah. Okay, this question, like, it wasn't an easy true or false, but I mean, we should be very familiar with the definition of a coordinate vector and what it means. Okay, let's move on. Inner product, norms, and so on and so forth.
What about matrix representation?
We kind of did that, covering the dimension curve and stuff. I think, I don't know, do we want to go inner product norms and then eigenvalues, eigenvectors? Or, yeah? Okay. Because I have a nice problem for the eigenvalues. N plus 3. We are now at inner product. What does it mean to be orthogonal?
The inner product is
Inner product equals 0 of like two vectors and your inner product equals 0.
Yes. So. Now, true or false? Is this true or false? I turn this to an if and only if, is it true or false?
No.
So the other way doesn't hold, right? Okay. And then example, I can give, do you want me to give you an example of something that doesn't hold, something that's a norm space that's not an inner product space?
Infinity norm.
But I'm not gonna prove it because we don't have time.
Infinity norm.
So like the answer is false, right?
No, this is true.
So
This
it's
one is
only-
true,
It's only in one direction.
but the converse is false. And you can find examples. One would be this norm. So consider the space continuous functions A and B. I consider the norm f equals supremum of f t, where t is in A, B. You shouldn't be able to come up with something like this on the test. I'm just out of curiosity because I know people would raise their hand and say, give me an example. This is an example. Good? Okay.
It's true only in one direction.
No, there's no inner product that uses this.
And a norm is not inner product, but inner product.
And this doesn't satisfy the parallelogram inequality, and that's why it's not an inner product. Okay?
You know, that sounds like something Halen would say.
That sounds like something else.
The brings flashbacks. He likes his inner product.
Does he?
Yeah.
Okay. Let's go to eigenvectors. We have 10 minutes left. Okay. So this is a norm space that's not an inner product space.
Wait, you're not correct. Wait, you really agree with me.
It's the same chapter,
Can I erase this? Question?
Can I say norm space not in
Guys, I just want to hear your colleague shout for a second. Yeah.
Can I say norm space not an inner space because they might doesn't satisfy identity.
I'm saying this is true in this case. This is just one kind of example. You could come up with many. There are cases when it's true though, right? So you can't say it's not true in general. Or no, you can say it's not true in general. You can't say that it's not true for everything. Okay. Okay. Eigenvalues and eigenvectors. You guys showed that we could have eigenvectors and eigenvalues for certain transformations and certain matrices. I'm telling you, this is something you're not responsible for. I just wanted to give an example because you guys were bugging me about the last one that I didn't give an example about. So okay.
What is something?
Supremum. Have you guys showed that we can't have eigenvalues for a certain transformation? People not in my tutorial?
Yeah.
Okay, so if you're in my tutorial, you might see this again. We're just trying to go through it fast. So we could show that there's a transformation with no eigenvalues.
No, real.
No eigenvalues.
No,
I did it in tutorial.
Yeah, but in lecture we said that everything has an eigenvalue, but maybe they're not real.
But we're talking infinite dimension.
Sorry?
Infinite dimension. So okay. Let me put it up if you disagree with me. Then.
Okay.
So what does an eigenvalue really do? It mimics the transformation, right?
Yes.
So we want to show there exists some scalar in our field, here will be an R, such that T of V equals to lambda V, and then the corresponding vectors for which this works is our eigenvectors, right?
That's our A.
Okay, so let's set up the system of equations and see if this could actually, and this eraser strap. See if this could actually hold. Okay. So what's our left-hand side? It's just an element x1, x2 in our infinity, the space of all sequences, okay? And then the right-hand side will be lambda, wait, the right-hand side, the left-hand side will be this, sorry. And then the right-hand side will be lambda times x1, x2. Yeah, this will be zero after the transformation, okay? So if we want to equate them, we're going to have this. You're going to have x1, so lambda times x1, x2, x3 equals to 0, x1, x2, x3, right? We want an eigenvalue that's going to represent our transformation. Okay, so let's set up the system of equations. So that means we have, I'll erase this board. Yeah, sold. So that means we have lambda 1, or sorry, lambda x1 is equals to 0, lambda x2 is equals to x1, lambda x3 is equals to x2, blah, 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 blah. Right?
Yes.
Okay, well, let's work with this. This is true if and only if. What? If and only if lambda is 0, or x1 is equals to 0.
Yes.
Yeah? But lambda can be 0, because if lambda is 0, then our transformation is just a 0, 0 transformation. Like it's redundant, right?
Yeah.
So let's say lambda is not 0. x1 is 0.
Yeah, and then
But now x1 is 0, so we're replacing this with 0. So this is true if and only if lambda x2 is equals to 0.
so the same
Right?
thing keeps